I haven't gotten to do math in months, and it's a bummer. And I want to revisit this because this is so fun. So, really, I'm just going to be quietly writing stuff on paper. But I just wanted to basically say, first off, I understand the Catalan numbers now, or at least I have a couple of examples of the intuition. I haven't like derived it myself. I think that's a lot deeper than um so anyways, right now what I'm trying to get through is the understanding of the Catalan numbers that I understand are these things called the dick words, which are basically ways that if I hand you n pairs of parentheses, how many different ways can you write those together? And so by imposing this constraint that you basically can't place for any prefix, there can't be more, of a given dick word. You can't. I don't think it's dyke, but even that sounds bad. So there's really no way to say this word in English that's good. But anyways, if you have a word, any prefix, there can't be more closed parens than open parens. And by imposing that constraint, you get all this cool recursive structure to it. Because otherwise, you could just like place them however you want. But now you have to like make sure that there's structure to it. And so there's a couple of cool ways. First, you can interpret it as these parentheses. You can also interpret it as, and I actually really like this intuition. I don't understand this, and I like this one. So basically, you have this grid, and by going down, you make an open paren, and by going across, you make a closed paren, or something like that. And so here you get the, open, close, open, close, open, close, open, close, open, close. And here you get the open, 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 close, 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 close. And so then, but then there's actually interesting structure in that, because you can actually arrange them. So this, I don't actually understand the non-crossing partition one, really. Like, this diagram doesn't really help me all that much. So these are the non-crossing partitions. Anyways, what I wanted to say is that there's a Haas diagram. I like this. And so basically, what chat said is that likely what this is you define a partial order by using an operation where basically, like, this one is above this one at all, above or at equal at all positions. So let's see if I can show some code here. So I had to generate some code. So basically, and this isn't going to help that much. I'm just going to describe it. And so, you can see here at this point, it's lower than all points on this thing, and then here. And then you define edges on the graph. Basically, I guess the word that chat used is a cover. I've never even really heard that. But it covers it if it's greater than at all height positions, and there does not exist another path, word, in between it. And so then you get this like lattice. And so this is pretty cool. I like this. And this is pretty understandable. And what I'm trying to work on is, because last time I went through equational theories, I was kind of just like total vibing, thought I understood it, didn't, So now we're just going through this. So I guess the first thing to review, just if I'm going to teach it, is like, what is a magma? And I mean, you need to know some math if you're watching this to understand this. But basically, a magma is super general. It's a structure where you have a set and you have a closed binary operation, and that's like it. Okay, and then he defines a homomorphism and an isomorphism using this definition. And I think I've seen this in like groups before, but I played around with this a little bit earlier, trying trying to just find homomorphisms just by like enumeration or something, like, you know, like make a guess for what phi is. Like given two magmas. Oh, and one thing that you can do that's cool that I didn't realize, if you have a set with a binary operation, or a closed binary operation, a nice way to actually like list out the thing is not in like a truth table, but in a Cayley table where you basically make a little multiplication table where like the row has the label and the column has the label. That's a nicer way to do it. Anyway, so I was trying. So I probably need to come back to the homomorphism and isomorphism definitions. But one thing that they say, of course, and actually, if you're like mathematically inclined, the number of possible magmas of a set of size n is pretty easy to figure out. So, actually, do I have my iPad? Maybe I'll get my iPad so we can just like draw it out. That sounds kind of fun. I'll be right back. What the heck? Okay, all right. That was a pain in the butt. I found it. What is it called? TL draw. Okay. Let's just make the new one. Okay. So all right. So what we're trying to derive is the expression that they claim that. Hold on. Oh. Oh no, is it out of battery? Oh no, okay. Okay, so they claim that the expression is n to the n squared. I added too many parentheses. I got parentheses on the mind. Is the number of magmas on set size n. Okay, and the way that you see this is, and wait, I'm gonna go dark mode. Let's do this. Okay. And so let's just make like a little table. So let's say that we have like A, B, C, A, B, C. So this is called the Cayley table, I guess. I don't know. I've never heard of it. Anyways, so basically what we have is we have S cross S to S. This is the like, I think Tau uses a diamond, but I'm not drawing a diamond. That's a pain in the butt. But it's the magma op. My ops, brother. Anyways, so it has to be closed. It has to come back. So if S equals ABC, then we're gonna have three options here, three options here, three options here, three options here, options here, dot dot dot. So the point is that we have basically 9 things where we have 3 choices. And they product, right? So that means that we're going to have 3 to the 9. N is equal to 3, so we have 3 to the 3 squared. So this is the n to the n squared. All right, pretty basic, right? Because you have n up here, you have n down here, thus you have n squared in here. This is n squared. So then, and then you have for each n in n squared, you have... Anyways, so there's the derivation of that. That was really simple. And it's nice that they basically spent no time on that because it was pretty basic. Okay, now here, this one kind of threw me for a little bit of a loop. They said, up to isomorphism, the number of finite magmas of cardinality n up to the number of finite magmas of cardinality n up to isomorphism is the slightly slower growing sequence, 2489. Or no. 1329. As there are n factorial ways to rearrange the elements of a set of cardinality n. The number of non-isomorphic magmas on a set of cardinality n is at least this. So I thought that was interesting because I was thinking like, yeah, I guess it has to be at least because it can't be at most, because no matter what, you're going to get n factorial permutations of the set elements. So you always can quotient that out, but there may be additional. And so he says, it turns out most magmas are idem primal. Never heard that word. Which implies in particular that there are no non-trivial isomorphisms. So the number of non-isomorphic magmas is fairly close to this lower bound. And so I actually asked chat to break down the n equals 2 case. I think this is the n equals... I'm almost positive this is n equals 2. Even though it starts here. I think this is a 0 or something. I'm pretty sure that's 0. So for the n equals 2 case, you get... Because this is n to the n squared, you get... basically the what is it called, a Boolean lattice. You get this thing. I'm pretty sure you get this. No, I don't know. Anyways, you get what I'm trying to say though is that there are 2 general cases. Okay, first off, you only have 2 elements, so there's only 2 permutations. You either flip it or you don't, right? And so there was like 2 classes of isomorphisms. There was the like what is called automorphic self whatever that just maps the elements themselves, and then there was, I don't know, I have to dig into that more, but there was something about like you either flip it or you don't, and there's like 4 pairs where you don't flip and like 6 pairs where you do, and that's how you get the 10 from the 16. But I would be more interested in seeing as n grows larger, like how do you Like, what do the I think they're called isomorphism classes, but what do they look like? I don't know. Okay, let's keep going. I feel like this is still not like out of my depth. I can still understand that. Okay, we're literally at definition 1.2, so I should hope so. The free magma m sub x generated by a set x, which we call an alphabet, is the set of all finite formal expressions built from the elements of x and the operation. An element of mx we call the word with alphabet x. The order of a word is the number of operation symbols needed to generate the word. Thus, for instance, x is precisely the set of words of order 0 in mx. Okay. I mean, that makes sense. The only thing that I guess I'm confused about is... So let me just write it in my own words. So we have a... So the free magma mx generated by set x called alphabet is set of all finite. So I guess I'm confused of if that, like, okay, an element of mx called a word with alpha x, and the order of x equals number of used. Okay, this is what I wrote. Free magma mx generated by set x, set of all finite made from x and dot. It's called an alphabet. So x in mx is called a word with alphabet x. Order of x is equal to the number of dots used. Oops. Okay, where did we go? Okay, then he says, so x okay, so that actually all makes sense to me. The only thing I'm kind of confused about is the set of all finite. Is mx always infinite? I don't like that you can't select some of the tech or whatever. Because the set of all finite strings should be infinite? What is it? They don't say the word length, do they? I don't know. Sometimes you gotta bumble around. Be an idiot. So we'll get to this when we get to the Catalan numbers because that's coming up and I got confused by that. By the way, magma, I think, is my favorite. Okay, so yeah, it's infinite. All right, so I'm going to write a note. Oh, wait. I don't have my... That's what I thought. Yeah. Yeah. Okay. Cool. So even if... Okay, so this is actually a good example. Even if the cardinality of the alphabet is equal to 1, we can... mx still infinite. That's actually nice that it gives you like a simple example, because then you can be like, all right, it's clearly infinite no matter what. So we have, by order, we have n equal to order 1, we have x dot x, then we have x dot x dot x, and so on. X to the n, basically. You can't really say x to the n unless you assume... I don't know. It's a syntactic thing. It's not really math. I'm getting into some weird transfinite or what. I don't even know what that's about. Kappas. I don't know. When you see the kappas come out, anyone that's not a logician runs, I think. Okay, but that was helpful. All right, but here's where I get a little confused. Okay, for the sake of concreteness, we will take the alphabet to default to the natural numbers. For instance, if x is equal to the set 0, 1, then mx would consist of the following words. Okay, so I'm gonna write down this example too. Example mx. Take x to be equal to 0, 1, then order 0, we would have 0, 1. 1, we would have 0, 0, 0.1, 1.0, and 1.1. Okay, and so on. But then I counted this, and this has 16, which makes sense to me, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, but then they say something weird. And this is what I don't get. Lemma 1.3. For finite x, the number words of order n is Cn size of x n plus 1. So for finite alphabet x, so let's just start off. The cardinality of x is 2 because we have just 0 and 1. So then So then we have 2 to the n plus 1. So let's just try to figure out the order 1 case. So this is going to go to 4 for order 1. So then we're going to have, and C1 is equal to, I think C1 is equal to 1, right? So we want to do 2. So let's do C2. So C2 is equal to 2. Because I think this is still 0, is it not? I always get confused with these stupid offset things. But I think that's 0. So this is 0, 1, 2. So we have 2 times 2 to the 3, which is equal to 16. Oh, interesting. See, I would thought that this was just a simple power thing. But it's only a power thing because of the alphabet size. Okay, so we should try another example where x is equal to 0, 1, 2. So in that case, let's try to come up with all the words of order 1. So let's just enumerate. Why not? Actually, can we do the focus mode? All right, nice. All right, so let's enumerate. So the words of order 0 we know are just 0, 1, 2. So there's 3 of them. Now we want words of order 1. So first we can do 0.0, 0.1, 0.2. 1.0, 1.1, 1.2. 2.0, 2.1, 2.2. I think that's it, right? So that makes sense because C of makes sense since C of 1 equals 1. So so we get 3 to the 2 because n is 1. All right, now the words of order 2, this is where it gets weird because this is going to be fucking insane. Yeah, because we're going to have parentheses because it's not the case that so it's not an ASOC algebra. Oops. All right, so let's try n equals 2. So we're going to get 0 dot 0 dot 0. So I guess that, I don't know, is it possible? Okay, so like, let's say that like we have something, we have like 0, 0, and this is like a 1. Like maybe we do have 1s. Maybe we do have like what we were saying. Okay, so but then 0.1, this is 2 and this is 1. Like we could do this. We're allowed to do this. So in this case, this would go to a 1. So then we have 1.0, which would equal 1.0 is a 1. But then this would go 0.1, which is equal to 2. So these are different. These are different. Okay, so that's cool. That's pretty neat. So, okay, at least at this point, I understand why the Catalan numbers are in here. I don't. Okay, so now, so let's take, yeah, so let's say we have like, yeah, we have like, so C of 2 equals 2 because we have either A, B, C or A, B, C. And now if X, so now we have 3 here, 3 here, or let's just make it N, N, and N, right? So we have Cn times N, is it N? Well, hold on, there's two different things. There's the size of the alphabet, and then there's the order. And N is kind of the order. Okay, so we have, so let's see, how many options do we have? We're gonna have, so let's make this M. So let's make this M. So we're gonna say N is the order, and M is the cardinality of the alphabet. So let's just say that. So then we can like make some progress here. So is it gonna be, I guess it is going to be M to the N plus 1. I guess that makes sense because you have M to the 3 options for this expression. And this is kind of the general expression. But the thing is, it's not 3. It's really, like you have an operation here and you have an operation here. So you have N plus 1. All right, so we derived the expression for the number of words of order N of magma with a finite alphabet, I guess. So that's nice. I'm glad that we walked through that. So that makes sense. Okay, lemma 1.3 makes sense. Let's see the proof. I love that proof. I think our proof was a little bit better. All right, definition 1.4. Induced homomorphism. All right, this is probably where they're going to lose me because this is, I see pies, I see phi's. A little too much Greek for me, huh? Given a function f x to g from an alphabet to a magma. So first off, that seems weird. Given f x to g x alpha g mag, we say the induced homomorphism phi under phi sub f on the free magma to G is the unique extension of F to a magma what? Given a function F from X to G, from an alphabet X to a magma G, the induced homomorphism phi sub F from MX, the free magma on alphabet X, to magma G. So, okay, so what is the free magma? So the free magma is a set. The free magma is not a magma, right? Wait, what? Okay, yeah. I mean, yeah, fine. Okay, so the free magma is easily. That's just because magma is so broad. Because for all x, y in mx, you have that x dot y is in mx as well. Thus, since dot closed, we're good. We're good. Okay, that makes sense. Tao just being a little bit casual. He's just kind of a casual guy. Eh? Just kind of a casual guy. All right. Okay. All right. Fine. I guess. But the free magma is kind of like a syntactic only thing, right? Like. Yeah. Okay. Yeah. So yeah. Okay. The free magma is kind of like the syntax trees. That makes sense. Where the magma structure lives. I get that part. This part is simple. It was just the syntax thing. How real magmas enter, the universal property. Given an actual magma, G, and a function. Okay, wait, hold on. I want to read the official part of that. Okay, so let's get back to the induced homomorphism now that we have a clearer understanding of what the free magma is. The induced homomorphism phi sub f from the free magma on X to G is the unique extension of F to a magma homomorphism. So first off, let me just remind myself, a magma homomorphism is where phi x dot y is equal to phi of x star phi of y, where phi is a map between like G and H. Okay. I'll actually be pretty happy if, like, the only thing that I actually accomplish out of this whole stream is understanding this. Okay, let me try to read chat's thing. Let me give it the definition that they. Wait, hold on. Let me use the example. Okay. For the unique extension of pi to a magma homomorphism. Okay, so basically he's saying that we can also take a function between sets and extend it to be a magma hom. I guess? I don't know. So for instance, if f from 0, 1, which is an alphabet, to G maps 0, 1 to x, y, respectively, then is it literally just a rewriting thing? Okay, but these diamonds are actually different, I'm pretty sure. Okay, so he says if f on 0, 1, which is x, goes to some magma G, then, oh shoot, then if I say f where 0 goes to x, 1 goes to y, then we take an element, so 0.1 is an element of mx. So this is an element of mx. And this, I guess, is an element of G. This is an element of G. Similarly, we have like a something more complicated. 1.0.1 is equal to 1 or y dot x dot y, and so forth. If pi is a map between the natural numbers, those are some interesting examples. So what am I not understanding? That's like what we need to figure out. So I think the first thing that I want to know is what even is F? Like what does it mean? So that's kind of the first thing, is like mapping a set to a magma is confusing. In the example, okay, let me read this part. Given an actual magma and a function, there's a unique magma homomorphism. Oh, so that's kind of nice. So the first thing is that pi or phi f so that's kind of nice, actually. I wish he would have said that. He could have put that there. Is phi f of whatever is equal to f of whatever. Let's unpack it very slowly. What are the objects here? X is just a set of symbols. G is a magma. MX, the free magma. It's infinite. But this one may not be infinite. This one might be finite. Elements of MX are fully parenthesized expressions. Yep. We should picture variables, letters, all syntax trees built from those variables and dots. Some concrete magma where things actually live and combine. Yes. Okay, I love that. That makes sense. What is F from X to G? Given a function, okay. Yes, this means a function from X into the underlying set of G. Okay, so F maps set to set. Okay, good. Let's chill. You are choosing for each symbol in the alphabet, but like, could... All right, so we have... Okay, all right, let's get back to what F is. So, but the thing is, could F be, like, nasty? Could it be nasty? I.e., like... No, I think the definition of a function is that it takes... Okay, I'm guessing that's a stupid question, and it has to be total or whatever you call it. Okay. But what if... So now, okay, so that's my first question. Can it be nasty? The second question is, what if cardinality of X is greater than the cardinality of G? And what if X is less than G? I mean, obviously, the F works out fine. But I mean, like, I mean, I guess it doesn't even matter. But I'm just trying to get a feel for what the induced homomorphism is going to look like. Okay. But it is literally just a rewrite, it seems. What is the induced homomorphism? Now we have a map on the letters, and we have a big pool of expressions that's infinite. The induced homomorphism is just the evaluation map. Take a syntax tree, plug in the meanings f of x on its leaves, and actually combine them using the operator. Okay, dude, this is like pedantic in my mind. It's like, why the hell are we going through all this trouble? But it's like, I don't even want to ask this anymore because it's literally just like, sure, you need... Oh, this part's interesting, though. I didn't quite get this. So now if you have a map between... So wait, what was pi? So, okay, so pi star just applies pi to each leaf of a syntax tree in MX. Yeah, that's fine. All right, I actually feel better. Why this is important. The free magma is the universal playground of all formal magma expressions in variables x. The induced homomorphism story is the formal way of saying giving a function f to g is the same as giving a magma home. I think it's not actually pedantic. I think there's something else. Oh, actually, bro, see, now that's why it's important. Okay, this matters because terms live in the free magma. An identity like x dot y dot z, the associativity rule, is literally a statement two elements of the free magma are equal. So now a magma G satisfies this identity if and only if for every assignment f all for all f into G, the induced map sends those terms to the same element of G. Oh, interesting, dude. Okay, that's actually dope. Free magma is the freest magma generated by X. No relations except those, the ones forced by being a magma. Any magma generated by elements. Don't quite get that statement, but that's okay. Actually, I would kind of like this. I feel like I have to do a lot of examples. I'm pretty slow when it comes to definitions. Yo, someone, dude, why are you asking me some random math question? What, that looks like a matrix? You paste in some random latex? Determine whether is associative. Determine whether any element can serve as identity. Identify whether the magma is a group, a semigroup, or neither. Justify each answer clearly. No, I can't solve that. I don't know that. That looks like some. That looks like kind of an interesting question, but I don't know that. Okay, so the main thing about the induced. Okay, so I guess the thing that my takeaway of phi sub f is that if we did anything other than send elements of mx to g via applying f to leaves, then phi sub f would fail to be a magma homomorphism. Okay, that actually seems kind of chill. Let's make that precise and then do unless by luck it's the same map, it will fail the homomorphism law. Why the extension is forced. Because like let's say that G is like X, Y, X, Y, Y, X, Y, X, or something weird, which is like a right associative thing. Then if we took mx, the function phi would have to be some weird infinite thing, but we could take like, yeah. I mean, the induced thing is like just construction, right? No, that's actually the one that I did. Oh, no, it's not. No, it's not. That's different. Yeah, it's an or. Okay. Yeah, let's try the wrong one. I always like doing the wrong thing, I feel like. If we stubbornly try to define some map, psi, it agrees on the leaves, but then we force some weird, then it breaks. So it's not. So wait, between the underlying sets. Well, the underlying set of mx is infinite, right? Because yeah. Okay, I kind of get the induced homomorphism. All right, let's get to the law. Time to learn about the law, son. X set. Okay, so X set a law with alphabet X is a formal expr of the form W prime, where W and W prime are in the free magma, are words. Thus, one can identify laws with alphabet X. Okay, so laws in MX cross MX. Okay, that's fine. A magma G satisfies the law. Okay, so a magma G satisfies the law. You better satisfy the law, son. If we have phi sub f of w is equal to phi sub f of w prime for all f. That's where it gets crazy. For all f from x to g. Then the syntax, if so, we write g something that follows the law. So, so like if I take like a simple, like let's say G is like G is equal to the set x, y, and then star, where star is like this, and we say that x is x, y is y, and xy is x, and yx is x. Then because, I mean, this is just a single thing. Yeah, I was gonna do commutative as well, because commutative is nice because actually it's order one. It's an order one law. Yeah, that makes sense. Two is the equation. All right, this is last time where I kind of really lost the plot. Given gamma a magma G is a model of gamma G G double bar gamma if it follows all laws, I guess, or satisfies. Given a law E, we write oh, now it gets fancy. Given, oops, shit. Oh, damn it. Given a law E, we say gamma E satisfies gamma if every magma G that models gamma also E. This is really where I lost the plot. This compactness, push forward. Oh, God. Okay, let's see. How long have we been doing this? I might eat dinner. It's already 9. All right, an hour of equational theories. I feel like that's not bad, actually. Okay, that was pretty fun. There's a lot more to go. But actually, like, the basic theory of magmas, like, hey, man. This is kind of what I want to get to. I want to get to this derivation of the numbers so that they... Look at all these OEIS links, dude. But I'm going to eat. I'm going to go to bed. I think I have stuff to do in the morning that's not math.